A very good day to my lecturer, Dr. Ernie and Jeffrey. Today we would like to present the CFD assignment on fluid mechanics 2. So basically we are from group A. So now we can see our group members of this assignment. So yeah, first we have my fellow friend Lukman Hakim bin Kamaludwan. He's the one explain the result and discussion, and he also assists the simulation process. And I myself, Satishwaran Kanu, I'm the explaining the introduction and theory of the topic, and I also assist the process. And yeah, here we go. And my another fellow Imran bin Salahuddin is the one who set up and do the mesh of the simulations, and he also assists the simulation process. And my other fellow friend Raja Iskandar Sukaini is the one who explained the geometrical setups, and he also the one who lead the simulations. So we go for the introduction first. So first we see the objective of the CFD. So one of the objectives is to create a simulation of a laminar flow of the flat plate using the anti-software, and then to learn and accelerate the various steps in CFD during the approximation solution for the physical properties that involve. And one of the objectives is to understand the effect of different airflow velocities in the profile of the boundary layer formation. First, we see the introduction. In reality, a boundary layer forms in the flow adjacent to wall and a fluid passes over either because the flow sticks to the surface. Over the object, this boundary layer has an effect on the flow field. The study of the classical laminar boundary layers is crucial to understand its physical and verifying computational methods, even though most practical boundary layers are turbulent. Thus, in order to study the laminar flow boundary layer with much more accuracy, computational fluid dynamics (CFD) are used. CFD is the process of mathematical predicting physical fluid flow by solving the governing equations using computational power. CFD software analysis like anti-software, fluid flow, and its associated physical properties such as velocity, pressure, viscosity, density, and temperature are calculated based on defined operating conditions. Next, we see the theory of the topics. First, we see the boundary layer. As the fluid flow over the flat plate, the fluid adjacent to the surface is injected, the interaction between the fluid particles and the surface. This creates a region and distributed flow called PL, which is boundary layer. Introduced by Ludwig Prandtl in 1904, whereas he developed these theories. Viscous effects are contained within the thin boundary layer. The fluid in the region outside the boundary layer behave as implicit interdimensionally dominated flow. And next we see the viscous flow. The boundary layer forms at the leading edge of the plate and increase the thickness from the leading edge in the boundary layer thickness. The flow will start as laminar and break down translational before becoming a fully turbulent flow as flowing across the plate. Next we see the boundary layer thickness. So what is boundary layer thickness? So boundary layer is the idea assumes fluid transition from velocity at 0 at the wall that we call as a no-slip condition to the free stream velocity away from the wall. Boundary layer thickness is the distance away from the surface when the fluid velocity reaches 99% of free stream velocities. Experimentally, the boundary layer should grow proportionally to distance from the leading edge of the plate. So that's the boundary layer thickness. Next, we go for the laminar boundary layer. As mentioned, laminar boundary layer is the first stage of the boundary layer, so there cannot be a boundary layer without laminar section. The boundary layer will, in general, be laminar in the range of Reynolds number 10 to the power of 5. The range is merely engaged at the transition of the luminance depends on many factors, which occurs at a lower or higher Reynolds number. So next, we see how the process of CFD using certain numbers of datas. So yeah, here we go.
For the geometry part, first we select the fluid flow fluent part first, and then we go to the save and save the file name. We save as our group name, which is group A. After that, we click the save it. And then we click the geometry part and wait for a while after we click the new design modular geometry. For the geometry part, first we go to the sketching. Then we select the axis for the XY geometry. After that, we go to the setting, we change the grid, click the show into the part and also snap part. For the magnetic spacing, we set as 11 meter. For the minor step per meter, we set as 10. For the snap per minor, we don't change anything. After that, we click the draw and click the initiate. We start draw at the origin. Later, we will put the dimension that we want. For the dimension, we set h1 for the length and h2 for the height. Then we enter the value of H1 as 1 meter and V2 as 0.5 meter. After that, we click the XY plane and click the sketch 1. And we go to the concept and click the surface for sketch. And we click the sketch 1 again and click apply. Later, we will click the geometry. After that, we already have finished the geometry part. We can check it the validation, the green tick at the project schematic at the light of the geometry part.
So after opening the mesh package, let's generate mesh over the plate first. So click on generate mesh. As we can see, this is the default mesh. It provides a basic grid, but it's not sufficient for accurate results. To solve this, we have to refine the mesh to get better resolution and accurate simulation. So what we have to do now is assign face meshing over the plate. The face meshing is important because it creates a structured and uniform mesh over the plate surface. So you can see the mesh is now more straight. Next, let's assign sizing for the plate to control the number of grid points on each boundary. So right click on mesh, insert sizing, and apply on the top and bottom edge of the plate. On the details tab, change the type to number of divisions of 50. And then disable the capture of curvature and change the behavior from soft to hard. Now we can generate the mesh. So as you can see, there are more grid points on both directions, but the mesh is not detailed enough to capture the boundary layer accurately. So we need more refinement. So let's assign mesh sizing again, and now apply it on the left surface only. On the details tab, change the type to number of divisions of 60. Then disable the capture of curvature and change the behavior from soft to hard. And for this, we want the mesh to be biased. The bias factor is the ratio of the largest cell to the smallest cell. It determines how rapidly So now we can save the mesh before going to the next step, which is setup. So let's update the mesh. Click on setup to open the package. As we can see, this is the mesh that is already sent to the solver, and our solution domain now is divided into a computational cell. So to set up the model, we first have to check it. So select general and click on check so that the solver can notify and give us information whether we did a good mesh so that we can proceed, or otherwise if there is any error we have to redo them. So for model, let's under the setup model, let's click model tab and change viscosity to laminar. Then select materials, click on air, and as we can see, we have control over its properties. We can change it. However, let's keep the values default. As for boundary conditions and top boundary, let's start with boundary conditions. Click inlet and change the velocity magnitude to 1 meter per second. Then click far field pressure, which is the top boundary, and change the type to symmetry as it is easier for the solver to work with. Now we can move on to methods. Under solution methods, change the scheme to simple. Then select monitors and open residual monitors menu to control the accuracy of the solution. For example, this one from exponent -3, we change it to exponent -7. Okay, the run is now ready to be initialized. So click on initialization and change the methods to standard initialization. And then select compute from inlet. And as we can see, the value of x will automatically change to the velocity set at the inlet, which is in x direction. Now we can select run calculation and change the number of iterations to an large number. The number of iterations does not really matter as long as the solution converges. Now click calculate and wait for the solution to converge. As we can see from the plot, the x-axis is the iteration and the y-axis is the residual. There are 3 equations, which the calculation only stops when all 3 equations are smaller than exponent -7, as we already said, indicating that the converging is successful. So that's all from me, and now I will pass to Lukman for the results. Thank you.
Box, a rectangle box. And now for our step, we open to the contour on the top, select on that, and now we get the value. By clicking on this contour, choose the selection, which is the location, it goes to the symmetry too. And now for the contours, select anything, you can get the value. For now, I choose 50 as my value. Now, before we start on XY graph, we must select the line by clicking on the locations and select the line. We go to the option which goes to the point 1 and point 2. The point we use is where we want to calculate, which is we use on the end of the flow. And then there's the location I put as the mark, and then there are samples. For now, we can use many things, but we will use the 35 samples for now. After we input the line, now we go to the top of the screen, it goes to the charts, and then we select the chart 1. And then after that, we go to the general set of chart. There is type X1 line. We go to data series and X and Y. After that, we click to the apply, and now the result appear on the screen. After that, we go to the exports, which directly goes to the locations. We input the name of the file, and we go to the Excel. When we open to the Excel, we see there's value for the chart velocity and Y. We can use this as our calculation for some sample given. That's all for me. Thank you.